let me continue by following the following plan. So first, if atoms and enhancement via a model program for atoms, and then the examples. I mean, the way to think about atoms is like interpolation of three Koch theories. A, this is classical Koch theory. B, this is the non-commutative. Koch theory. And then C, Birational Koch theory. So, and so we saw these examples yesterday where you have this F bundles where the base are all PP cycles. So then the fibers are they're homologies, which of course can be interpreted as a non-commutative Koch structure. But on this non-commutative Koch structure, you have a splitting using the quantum multiplication. And then, so you have this Euler field, which gives you this spectral coloring, and the sheets of the spectral coloring precisely correspond to the eigenvalues of this quantum multiplication. So now, this is the picture which we explored a little bit yesterday of some examples. And in some examples, we saw that if we actually want to do G non-rationalities, basically what you do is, instead of looking at all base at PP cycles, you restrict yourself to the ones which are G equivariant. And this means that you strongly restrict these PP cycles to equivariant PP cycles, and then it just means that the corresponding base is much smaller, so that some of the eigenvalues come together. You are keeping the ramification divided in a strong way, and that's why you change non-rationality phenomena appear in the case of rational varieties. Now, I will start looking at this with a very simple example, and that is P2. Now, and I'll add a little bit to the theory of P2, since we want to go deeper and eventually formulate enhanced model programs. So, of course, for P2, we have three eigenvalues. And the right way to think about P2 is to think about its Landau-Ginzburg model. And this is the function x plus y plus 1 over xy equals w. So, I mean, if you look at this function, if you create the denominator, it actually has three singular fibers. I mean, it's a vibration of both elliptic curves, and it has three singular fibers at the third of the period. So it's an elliptic vibration, the vibration of polynomials of degree 3, parameterized by W, but so you can compactify this, and you can even compactify the fiber at infinity, and so by Moshe's theorem, so if you have a vibration of elliptic curves, so it will have 12 singular fibers, but so if you want to put this at fiber at infinity, you will have one A9 singularity here, so you have 3 in the finite part, and you have 3 singular fibers inside. And so what does it mean to actually blow up a point on P2? So in terms of Horst diamond, we just add one more cycle here. And then what's happening here is instead of having K9 at infinity, you get one more fiber here. It's the final part, and you have A. And so the fact that we've blown up one more point corresponds to that we actually created one more singular fiber. And so then we increase our coloring, which had 3, was 3-sheeted now because we introduce one more singular fiber, it becomes 4-sheeted after this blow. So now the whole point of theory of atoms and trying to realize if something is rational or not, to find some conditions when these things which are inside do not come from infinity. So now let's go to dimension 3 and consider an example that was discussed today in advance, sorry, quite a bit. And so if you take the P3, the corresponding potential corresponding quantum Gensburg model looks like that. So it's a family of K3 surfaces, and it has 4 singular fibers. And so you have a very complicated compactification consisting of 36 rational surfaces at infinity. And so now let's look at the example of intersection of 2 quadratics in P5, which was considered today. So, I mean, in terms of Landau-Ginzburg model, that's worked out in detail in a paper I wrote with Denis and Mohammed a long time ago. It's a Birational. So, what the effect of this blowing up of this genus 2 curve, which is intersection of 2 quadratics, is that you actually take from this very complicated configuration at infinity, and you put so it's a intersection of 3 hypersurfaces, 3 rational hypersurfaces, into this genus 2 curve, I mean, the generated one. And so that's what you actually bring from infinity. And so then, of course, in order, so this thing has, this is the intersection of 2 quadratics actually blown up with an additional point, but if you squeeze this quadratic, which can say it is triple, so these things are actually going back to infinity. So this is what is actually the corresponding Landau-Ginzburg model associated with the 2 blown up this genus 2 curve. So there are things which cannot come from infinity and things which are blown up which come from infinity. So in a way, we have interaction of 2 minimal model programs. One, which is in the finite part, and it cannot come from infinity, and the other that is the classical birational geometry, things that come from infinity. Let me give you one example where you have a so this is the Landau-Ginzburg model associated with three-dimensional qubit. And you have very complicated configuration, this intersection of three rational surfaces in open book configuration, and then three other intersecting them in a transversally, and then you have two other K3s, and so some complicated configuration at infinity. And so the point here is that this configuration cannot be brought from infinity. Now, this is all how we want to think about, but we cannot think about this like that. So we want to forget about the Landau-Ginzburg model and still, in some way, recall and scientifically think about these configurations which cannot come from infinity. And in order to do this, we kind of introduce non-commutative linear systems. And so this is developed in two papers, one with Liu and one with Harder and Liu. And so basically this non-commutative linear system are connected with the solutions of the quantum differential equation. And solution of this quantum differential equation are expansions which give us the Gromov-Witten invariant. But so now what we are going to study is, so I mean, in classical geometry, you study the base loci, or to precise singularity of the base loci associated with the anti-canonical system in the case of Fanon. And so now the analog of this is actually the asymptotics of sub-exponential growth solution of this quantum differential equation. So you have some terms which have sub-exponential growth solution, and so this is actually the singularities of your system of solutions, and so we will think about the solutions of this, the asymptotic of the solutions of this quantum differential equation. Now here K is nothing else but the matrix of the quantum multiplication, which appear in the considerations of Giovanni and Pedro already, and this is some grading operator that we can associate in this case. So the singularities of this system, of this D module given by this differential equation, actually are connected with the monodromy of around this fiber that we have here. So in fact, there is the first statement to connect this with rationality, and that was a theorem that we proved a long time ago with Zoltowski, and that is that consider these Landau-Ginzburg models, which for Panos are all computed. Yeah. So, and then in this case, so you have all these Landau input models, and so we have some very singular fibers, and then you have this monodromy around the very singular fiber, which always corresponds to some fraction of RBL. And so the monodromy mu acts on the delta part of homology of this generic fiber after we compactify. And so you have in the Picard one case always some 3x3 matrix. And so basically the statement is that if X is rational if and only if this matrix is strictly unipotent. Now, this theorem is kind of stupid because the way it's proven is you know all this Landau model, you know this classification of Skorsky, and then you just compare. That's what's happened. And now, I mean, what we will try to do now is to give a conceptual understanding of what is happening here. And so indeed, one can translate this statement in the language of this asymptotics here. So this statement is equivalent that so delta is equal to 1 if and only if this is rational, sorry, potential is rational, if delta is equal to 1. And so in all other cases, delta is bigger. What is delta? So this is this asymptotic. If rational, if delta is equal to 1, and in all other cases, delta is bigger than 1. So that is the conceptual understanding, conceptual translation of this statement, purely done, of course, on the language of Grom-Witten theory. So, and that tells us that if you have something in this quantum differential equation, if you have the singularities, which actually are related to what this quantum differential equations are actually given with related to solutions which have sub-exponential growth bigger than 1 in this case, then this cannot be actually obtained by a blow-up. So this thing is not rational. So there are things inside which are connected with asymptotics which are bigger than 1. And of course, you can blow up and you'll get something with asymptotics equal to 1, like in this case. So these are things which relate to the birational geometry of this particular funnel. So the things that you can obtain by blow up. And there are things that you cannot obtain by blow up just because their asymptotics are bigger. So
when you talk about sub-exponential growth, so the solutions are written around the point of infinity of these pictures. Mm-hmm. So that's the asymptotic that you're saying determines.
So, of course, there are several asymptotics. I'm talking about the biggest one, but they are related to each other by this grading open. So, so this is the general picture that we have here. So it's the asymptotics of this differential equation. that
Can I ask you another question?
Yeah.
Sorry. Okay, so rationality, as you said, this corresponds to this phenomenon. If you can move away a part of this, how is that? Why is that related to this delta being one or not being one geometrically?
Yeah. So I mean, in a way, I think this delta is nothing else but the self factor associated with this
I see.
category, and that's the monoidal. That will save the spare. Yeah. I mean, that's the delta in the case of three-dimensional cubic is actually equal to 5/3 if you just compute. And then, as I said, this is the self functor associated with acting on this piece of the splitting. And so, I mean, if you assume that this is a piece coming from the genus 5 curve, we do know how the self functor acts on genus 5 curves, and certainly it's not like this 5/3, and so this gives you to say that group of atoms. And now, but so this is the picture mass of the paper with Max and Tony. So now we want to enhance it a little bit by getting the minimal model program involved into this picture. So now let's look at some more examples so that we get how against that.
But in this case with visual posting, this was done just by kind of checking the list.
Yeah.
Right.
As I said.
General.
So let me give you a formula for computing this delta for Fano hypersurface. So let's say that X is hypersurface that is much more general formula, but let me just mention the easiest. Degree D in Pn. So then delta is equal to dimension of X. For the cubic. All right, so now, but if you look at the four-dimensional cubic, so I have degree 3 in P5, then this formula is, what is it, 4 So that's not good because it's equal to 2, and actually the theorem is that x is rational if and only if delta is bigger than the dimension of x minus 2. So in the case of four-dimensional cubic, this criteria doesn't quite work because you have delta be equal to 2. And I mean, as we know, you need to go deeper.
But if and only if, right?
Yeah. Sorry, I put it.
It's rational, then that's not.
Sorry, if so in this case, on the four-dimensional cubic, we cannot apply this, and so you need to go deeper and look at the number of right cycles associated with the corresponding answer. So now, still, there are other cases where you can apply this, and let me mention some of them. So let's consider the case of degree 4 hypersurface in P5. So what we get in this case is delta is equal to 4 Yeah, so in this case, of course, this is bigger than the dimension of x minus 2. So this is how one concludes that generic four-dimensional quartic is not rational. So similarly, for d equal to 5, so we have 4 minus 2. And so that is certainly bigger than, let me actually compute it since.
It grows with degree. So it's
Yeah, but there will be an application so that, so we have 4 minus 2/5, so it's 18/5. Yeah. Now, so I was asked by Vanen Chortsov, sorry, by Jigun, about the following. I was asked the following question: what can we say about x4 plus x4? So where x4 is this notorious quartic fourfold, sorry, threefold, and x5 plus x5, then And so this is birationally rigid as proven by Skolsky and Mare, and this, if I'm not mistaken, by Puknikov. I think this was his master. I was there when
Published
he defended. This will only tell you how old I am. And in any case, so I mean, if you actually compute delta, I mean, in this case, it's for the quartic.
The product.
Huh?
The product.
For the product, yeah. So it's equal to 5 halves plus 5 halves. The dimensions are additive. And that, of course, is 5, and it's certainly bigger than, this is something of dimension 6, so it's bigger than 4. And that's how you can put that this thing is birational, and it's not rational. And similarly here, so you have delta is equal to 36 fifths, which is bigger than 7, bigger than 4 plus 4 minus 2, 6. So that's how you can put that this is not rational. So now I don't know how to talk about rigidity, but might be connected. I'll say, but definitely these are two examples that the Puknikov method due to Fano Noether inequality works for with the group being bigger than 6. And so now I must say that this method is going to work for all different kinds of products as well and not it, and so the dimension just get bigger and bigger, and so for this you can prove that I'm not saying anything about rigidity, but no rationality. This method.
Do you have the theorem for weighted?
Yeah.
How does it?
I mean, one I don't remember. I mean, so it's formula, but you can do it for functions. I mean, in fact,
No, for weighted hypersurface.
yeah. I need to.
I'll put these slides for tomorrow.
So I mean,
Okay, good. For weighted hypersurface.
it's part of GKM. So.
Put some of these slides.
There is nothing.
But is it like a simple formula?
Yeah, it is. I mean, in fact, all right. So this is just what this asymptotics already give you. So this is the way I think about this asymptotics is like proposal for what makes minimum model program should be for algorithms. Now, of course, this is really not a joke. I mean, so I'll really try to convince you that there is something into it by going in a little bit more intricate example. So the first example we'll look at but we want to really use minimum model program, we need to go to dimension 5. Because I mean, this is where the minimum, the codimension 2 fixed. The minimum model program makes well, certainly. I actually took a course with Miles Rick in 1984 as MI6 representative Miles versus Moscow at that time. He did, as a color, he did teach a course on minimum model for surface. It's a fantastic course.
In English?
No, but he speaks Russian.
Oh, okay.
No, but it takes him like 2 weeks and then he's pretty good. then he forgets it. So, in any case, let's consider the intersection of quadratic and cubic in P7. So now this funnel is course diamond which looks like that. And so this is a very famous piece, especially for physicists, because this Horst diamond is nothing else but Horst diamond of mirror of a rigid Calabi-Yau. Rigid three-dimensional mirror of the rigid three-dimensional Calabi-Yau. So rigid means no deformations, and so that's why you have I'm not writing the zeros, but so this is the the mirror actually this rotates, and so this 2-1 part goes here, and so now this rigid Calabi-Yaus, I mean, if I remember Max Kreutzer telling me that he gets like 3,000 something examples in dimension 5. This is what he calls funnel Calabi-Yaus. Calabi-Yau which is contained post diamond of the funnel, but it's single. But the smooth ones, if I remember correctly, I think that's it. I wrote the PDF. They're either this intersection of quadratic and cubic, or the double solid, 5-dimensional double solid ramified in a quad. So in the 4-dimensional, so in P5, P4. So, but in any case, let's stay with this one. Now, we are very much like in the situation of 4-dimensional cubic, because this is something that we want to claim it cannot be brought from infinity, and there is an obvious abstraction to this, that it has very few algebraic cycles. So only 2. But I mean, we really need to argue this properly, and that's what we are going to try to do. Now, so, I mean, of course, this has the first thing to try to do is so that's what Lana was asking me. So, I mean, actually, in this case, when you have a complete intersection, the formula is as follows. It's n+1 minus d1, so whatever in this case, minus d2 over d1, where d1 is the biggest, yeah. And so, so it's 5 minus 2, 8. So, it's equal to 3, and that's precisely that it's actually Calabi-Yau. To get technical dimension. It's the fractional Calabi-Yau always, but in this case, it's just actual Calabi-Yau. That's what And so, but, so let's argue as follows. Assume that we brought this from infinity. So therefore, it corresponds to algebraic variety. Now, if you compute with GKM algorithm that was discussed, you are actually going to notice that this has so index is 3, so it has indeed 4 eigenvalues of the quantum multiplication. And so this thing here that you have actually correspond to just one eigenvalue. It cannot split any further. So if you move over this base, you're on the right side. So now assume that we were able to carry it from infinity. In other words, that this corresponds to the lower. So it is like a Calabi-Yau, but it might be singular. Now, using minimal model, so this assume that this is a minimal model program, but minimal model, but it could be singular. But in this case, these resolutions actually will be done only by extremal constructions, which bring curves to a point. The fact that this Calabi-Yau general type tells you that you have extremal contractions which only contract curves to a point. This is a work of Alessio and Fulgius. No,
even applied to Calabi-Yau.
Calabi-Yau general type. Net is enough.
I mean, you can resolve it by small resolution.
Yes.
Which Calabi-Yau?
I mean, assume that I have this Calabi-Yau.
This specific.
So now this is really a combination indeed of this statement for, of course, to make sure that I'm right, that I run this argument for pianos.
But maybe it's even smooth.
Yeah, it's possible. Then there is no problem. But I mean, the thing is that you really need to go to a smooth one, because what you want to show is that even if you resolve this piece that is going to have four algebraic cycles, actually stays fixed. In other words, whatever you add by this resolution, you are always going to have piece corresponding to this quantum multiplication that is going to have four algebraic cycles. There is no further splitting. And so if you have this thing, assuming that counts from algebraic variety, even after the resolution, it will preserve at least four algebraic cycles. And here we only have two, no matter what we do. So there is no way that this is actually coming from any algebraic variety. So the important part that it's used here, I mean, so Ron-Witten theory is used in a big way here, because I mean, if you do the curve counting, these are only curves that are getting contracted, so their modular spaces are going to be of dimension 2, because this is a Calabi-Yau, so this is also going to be of dimension 2, and so real, so 2 plus 2 is less than 6, and so they don't interact, they don't intersect, so this D module, quantum D module associated with this situation is uh, preserving this splitting. So that's the important part that is wrong with M theory here. There is no further splitting. This piece gets preserved. In other words, the quantum D module splits like that. And so this piece, the 4 algebraic cycles, actually survives. So there will be 4 algebraic cycles even after the resolution. So there is no way that the thing that we have here, our splitting, comes from algebraic variety. So I mean, it's a little bit of a modification of the argument for the three-dimensional cubic, sorry, four-dimensional cubic, but with some use of minimal model program and this counting of information of this curve. So now one can extend this to dimension 4 using some advanced work of Pardon, but since it's very tricky here, and I don't really, of course, he's a hint of the transversality statement. And indeed, it's very tricky because it's, in this case, 4-dimensional real varieties, and so it's 8-dimensional. To move it, it's very tricky, but so I don't completely understand this like in the 3-dimensional case. Go into this right now. But in any case, so the point I was trying to make in the following. So in fact, there is a suggestion here that you should try to combine the two minimal model programs, maybe one. And so first is develop a minimal model program for mixed atoms. In other words, so you have these pieces that appear in the corresponding decomposition coming from the quantum multiplication. So in the same way, we understand the minimal model program in dimension 3. So we can try to classify them by putting in association with them some invariants. So the first one is this delta that I mentioned. And then, of course, there are other deltas that are going to be appearing here, except other symptotics. Then, of course, you have the defects. This is something that was initiated by Clemens a long time ago, and a beautiful work which was never published by Ansu Gilles. I mean, that's their thesis.
Maybe it was.
No, no, I mean, I wish, no, but I just asked them so very recently to you. That's but the thesis exists, and it's very well. And so, I mean, some parts, yes, probably. But, you're telling me you know more. All right, I want to know. So in any case, so this the defect, and then of course this defect is the failure of concurrent duality between H4 and H2. I mean, probably there is additional structure, and even she indicates that. But of course, this is in dimension 3. So if you go to higher dimension, there will be other defect functions. So there will be more failures. And, So that will be giving you classification of this um, atoms that appear there. Now, monodromy is going to have different action, and so this asymptotics are going to be enhanced. You have not just a sequence of numbers, but pairs, triples, and so on. So it's getting interesting. I must say that this was predicted some time ago by Libgover, and so it's not that people didn't think about this. And also Mustafa is not related to this, but thresholds. And so this is something that comes from the species inside. And then there will be just classical minimal model program. And so these two theories together should give you some new thinking of birational geometry of your variety. So it has to be pairs. And then, of course, so Vanya seems to be putting down everything in G equivariant, but I don't think so. I mean, so there is a lot to do there. Meaning, for me, G minimal model program and the classical ones are very different from this perspective because indeed, I mean, G part on these atoms that come from the inside is going to be quite significantly different. And so if you put this, I mean, so G here, so this is a completely different story when it comes here. Maybe indeed on this classical part, they are not much different, but when it comes to this part, which is associated with these atoms of the inside,
The proofs are the same. Even people usually don't even bother to write down what you said.
yeah, I've seen this Scholar Mori book.
They said it's the same.
Well, no, but I mean, so the truth is that they don't say that. So they say the following. I mean, I actually went to look very recently. So they say that we changed the field, and therefore, because the Galois group appeared, so this is like the over this field, but the Galois group is there, and so that's the way to think about the G equivariant. Like you change the field, and then this Galois group appears. That's what they say.
The group is fine and everything can be done equivalent to the same way.
I mean, I believe you. So, but is there text which this actually was written in detail?
Usually 3 months.
That's it's not only you that is putting it down. That's what you're saying. So you don't want to take responsibility. But I mean, in any case, so I mean, maybe indeed there's not much here, but from this perspective, I mean, so things which are on inside, I mean, these are very different. So I mean, I think that that is what is worth pursuing. So it's just trying to advertise that this combination of so far it was basically combination of these 3 type of Koch theories, which already produced some results, but you really can look deeper, and then the combination of minimal model program with some rather advanced Rom-Witten theory can actually give you more results. I'll talk more about this in the Brazilian, but I'll stop here.
More questions?
So for weighted hypersurfaces, is it like already written somewhere?
I mean, I must say that this SAGE program that we were writing, already the formula is written there, so I just don't remember. I mean, for me, remembering this coach diamond is already a challenge. So you want them to remember. No, but I mean,
But for example, what the salary is for quadrics? Quadric. If you have quadric triple with no, with a group actually. With a group you don't.
no,
Oh, yeah, no, it's-
We don't know it. Oh, okay.
no, I think indeed it's possible, but it's not, that's the thing. Because, so just think of what's happening. And so if you have a group action, several of these fibers are coming together. I mean, what is this? It measures the monodromy around this fiber, but if several fibers are coming together, it's a completely different monodromy. So,
Quadric reported visit action with idempressing, nothing works.
so I
But
mean,
for weighted hypersurfaces, you have a formula in terms of degree and weight.
It's similar to that one, but I tried to find it, so what I could.
Okay.
uh,
Good.
But for quadric, it was never got it.
no, quadratic is going to be, just three-fold is going to be just one.
Ah.
I mean, yes.
So this argument here, it's still, I mean, the Landau-Ginzburg, it's just in the background,
Yeah.
as inspiration like before.
Well, I mean, yeah. So Landau-Ginzburg is replaced by the quantum differential equation. So the singularities of the anti-canonical system, but in a way, so they are these singularities which are measured by the infinite part. But so now the way to think about this, so what is happening categorically, so what's the analog of sections of the line bundle? It's the natural transformation. So you have the corresponding functor, and they are natural transformation associated with it. So this quantum differential equation actually measures singularities of natural transformations, and so that's what this delta is. And that's actually explained in this paper with Albert. And also Paul, long time ago, actually noticed this as well. So this work with Birational that they have started to work out. I mean, his approach is different, probably much more scientific, but that's what he did for some time. I mean, he has a sequence of papers, and one of them is not.
And these numbers there, you said they're more asymptotics.
Yeah. I mean, so you should think of this as follows. I mean, so these are like homologies project. So, I mean, what you are doing here, you are modeling massive quantum field projects, conformal field theory associated with this model. So, conformal field theory has something which are called R charges. And so the central charge is this delta. So there are other charges, but we can compute one for another. So now in this singularity cases, which one is asking, that's a little bit more dangerous. Because I mean, this massiveness, if you have bad singularity, is kind of lost. It's still geometric, but it's not exactly variant. And so in my, I don't know that much about conformal field theory, but so I've read some books, but if you move this massiveness from what I know is you still can compute the R charges, you buy a ticket to Stockholm. So it's really hard. No, I mean, this is McCoy, this Barry McCoy guy. It's not John. He's
Okay, here, small break.
Let's get like 10 minutes.
Right,
So
right.
5 minutes.